Hi, this is Mark Weitzman. Welcome back to Quantum Field Theory: A Student's Perspective. Today I want to do a recitation on a problem from Borkin and Drell. We're going to do, this is the lesson 3. This is our 4th video, recitation on the formalism. Sorry. Whoops, easy. This is for a formalism for the massive spin 1 particle. When I say formalism, I mean the canonical formalism. And we're only going to be doing the classical today. And this is actually a problem from Borkin and Drell. Chapter 11. Now, I understand that most of you have not seen a massive spin 1 particle or even have any idea of how to handle it. It's also called, I believe, the Procca equation. But we're just going to give the wave equation, just going to give it as a given. The wave equation for a massive spin 1 particle. I believe it's also known as the Procca equation. And the equation is G mu nu is just our usual Minkowski metric. Borkin and Drell used G instead of eta. I'll define box again, but that's the usual, the Albertarian, how we pronounce that, in 4 space-time, flat space-time dimensions. So our field is, let me just define box as just and this is just equal to second partial with respect to T2 minus del squared. The field is phi, 4-component field. But as we'll see in a second, when we start getting into higher spin fields and everything, there are usually subsidiary conditions, often called gauge conditions, which you're probably familiar with from electromagnetism. So here we'll see already that even though we think we have a 4-component field, we actually have a 3 independent components. But we're gonna work through the formalism as if we have 4 components, and that will be a subsidiary condition. So the equation has a built-in, let's call it a divergence condition. It's a 4-dimensional divergence. You could also think of it as a gauge condition. This is the partial of phi nu. The covariant divergence is 0. Okay, so the first part of the problem is we should at least show this. To see this, apply. Now notice there's only one free index in the wave equation. Nu is summed over, so this is an equation. This is 4 equations. The free index is mu. So apply the partial with respect to x mu to wave equation. Okay, so we're going to have box, the partial. Actually, I'm going to apply the lower one. G mu nu box plus m squared minus partial with respect to x mu, partial with respect to x mu, partial with respect to x nu, phi nu x equals 0. So this becomes, when we apply g mu nu to this, it just replaces mu minus nu, and it lowers the index. And this is an upper index because it's in the denominator. Downstairs in the denominator is upper. So this is going to end up being, this problem, by the way, tests your handling of signs and index gymnastics, so it's kind of good practice. So we have the partial with respect to x nu, the box applied to phi nu x, plus m squared, the partial of phi nu x with respect to x nu. Again, the g mu nu just replaced the mu by a nu and raised it, or lowered it. Minus, now this combination over here is just a box. So I have minus box partial of phi nu x with respect to x nu equals 0. So these two terms, the derivatives here and here, they all commute, the box with the x nu. So you can see that these two terms cancel. And the m squared is positive, that cancels, so we're left with the partial phi nu with respect to x nu equals 0, which is what we wanted to show. Okay. The first part of the problem is to construct a Lagrangian density. Now, as I mentioned earlier, a lot of times you can just eyeball it and figure out the Lagrangian density, but I'm going to go painfully slowly because there's a lot of indices and things going on here, and I'll construct it by what in one of the lectures, I said you multiply by del phi variation and then you integrate. So we'll have the integral from t1 to t2 dt, the integral of d3x, del phi mu, this is the variation in the field. Then we multiply that by the wave equation. Okay, and this will manipulate this. Okay, the g mu nu again is going to lower the mu index, so I'm going to get del phi nu. I'm going to expand out the box here. I could use any index, but now that mu is gone, I can use mu again, so no big deal here. I have plus m squared del phi nu x. Now, over here, what I'm going to do is an integration by parts. I'm going to apply this to the left over there. So that's going to change the sign, and the del and the partial derivatives always commute. So I'm going to have del partial of phi mu with respect to x mu times this term, which still remains, partial of phi nu with respect to x nu equals 0. Now, you'll notice I'm not going to use the subsidiary condition. Basically, we never use the subsidiary condition except when we get to the equations of motion, or just to verify them. As I said, when you actually do the quantization and everything, this always leads to choices of gauge and some interesting difficulties, and we'll go into all that stuff later in the course. Okay, so this implies now here, again, I'm going to do another integration by parts by applying this to here. So it's going to give me a minus sign, partial of phi nu with respect to x mu. I'm sorry, and we have delta of that, partial of phi nu with respect to x mu. Now I'm going to write this. This is easy to see. Del phi nu. Sometimes I put in the argument x, sometimes I don't. Okay, so it's obvious when you take the del of this, you're going to get phi nu times del that, plus, you're going to get two terms. I left out the half here, which reproduces that. And then I'm going to get, and you can also see the same thing here. We have both of these terms are the same. I use different indices, but you can see we're summing, so it's both the same term. So I have 1/2 del partial of phi nu with respect to x nu squared equals 0. Okay, so now we have the integral from t1 to t2 dt, the integral d3x. Now we can take the del of the whole thing, minus 1/2 partial of phi nu with respect to x mu partial of again, these two terms are the same. I mean, you can figure it out that the raising and the lowering of indices doesn't change the terms there. Then I have plus m squared over 2 phi nu plus 1/2 partial phi nu with respect to x nu squared equals 0. So all we've done there is I've just taken the del of the whole thing out. I don't know why it does that to me. Okay. And so this implies, this is basically our answer. So from this, we get our Lagrangian density, minus 1/2. Okay, so let me put a box around this nice Lagrangian. And, if you look at it, it looks like electromagnetism. It's not quite because phi is a vector field, but, if you looked at electromagnetism, you would have, this would be A, phi would be A. So this would be partial A nu with respect to x mu. This would end up being the, the field term squared, fu nu. And this would vanish. And for electromagnetism, m equals 0. So we're not going to have this term. This term breaks gauge invariance for electromagnetism. So we can't have it. But for a spin one, we can, a vector spin one. Okay, so our second task now is to construct, using our formalism, the Hamiltonian density. Okay, so let's rewrite. Usually when you do the Hamiltonian density, the only thing you're interested in isolating the time derivative terms. So let's get the time derivative terms out of here for now. So L, you could see that in the first term here, the time derivative, we set mu equals 0. And so that's just going to be, and then we could have nu equals 0 as well. So that's going to be minus 1/2 phi dot the phi 0 component, time derivative of the phi 0 component squared. And then the spatial things, again, we have mu equals 0. These are both, doesn't matter for time where the indices are. But for the spatial, the i's, these have different signs. So this becomes plus 1/2 phi dot I squared. And now, so that takes care of the time derivatives there. There's no time derivatives in this term. And there are some time derivatives in this term. So we get plus 1/2. Now, when we take nu equals 0, we get phi dot 0. So that's a time derivative term. And then the rest of this expression is just plus the partial of phi I with respect to xi. This whole thing is squared. These are time derivatives because this one squared is a time derivative. When we multiply by this, we'll get a time derivative. And this thing by itself won't be a time derivative term, but we'll take that into account. Okay, plus dot 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 non-time derivative terms. Okay. Now, as usual, we define the canonical momentum here because we have a vector object. We'll have a vector object defined, although the canonical momentum is usually reserved for the time one, but we're just going to define this covariant as the partial of L with respect to phi dot u. So let's just plug in for the terms. The true canonical momentum, pi 0, is equal to the partial of L with respect to phi dot 0. So let's take that. That's why I wanted to isolate this. So this is equal to minus phi dot 0. And then when we take the derivative of this term, we get 2 times a half, that cancels, times this term. And the derivative of this term with respect to phi dot 0 is just 1. So I get plus phi dot 0 plus the partial of phi I with respect to xi. So these two terms cancel, and it's just the partial of phi I with respect to xi. Okay. We box that equation. Okay. And pi I is equal to the derivative of the Lagrangian with respect to phi dot I, the derivative of the space components of phi. And this just comes from this term over here. This is equal to phi dot I. Okay, so we'll box this as well. Okay, so now by definition, our formalism says that the Hamiltonian density is equal to pi mu phi dot mu minus L. So this is equal to pi 0 phi dot 0. Okay, let me keep L in sight over here. Pi dot 0 phi dot 0. And then I'm going to have no idea why that shows up. So now I'm going to have phi dot I squared. I'm just going to replace, so I'm going to get pi I phi dot I, but phi dot I is just equal to pi I. So I'm just going to get pi I squared. And now I have to subtract all the Lagrangian here. So it's minus this. So I'm going to have plus 1/2 phi dot 0 squared. And okay, I want to go back to the whole Lagrangian here. So when we have this term, I'm subtracting this term, so I got plus 1/2. The first obvious term is phi dot 0 squared. And then I get an index with an I down, and a nu is 0, and an I for mu. So that's the I is going to give a negative sign over here. So I have 3 negative signs, one from there, one from the minus L, and one from the I's here. So I'm going to get an overall minus sign. Notice I put the I's in the same thing. I've taken into account there. And now I have the, when I have mu and nu is I. I'm sorry, when I have nu is I, but mu is still 0. So I get minus phi dot, taking time derivatives here, minus phi dot I squared. And then I get a plus partial phi I with respect to xj, partial of phi I with respect to xj. So this is just when I take mu equal I and nu equal j outside of the time things, then again it's an overall sign here of, you know, 1 minus and 1 minus, the two negative signs there cancel. Okay, so that takes care of that part. Now I'm left with this part, these two terms over here. So I have minus m squared over 2 phi 0 squared plus m squared over 2 phi I squared and then I have one more term. I've left out this term over here, minus L, so I have to subtract that term. I haven't yet done it yet. So I have minus 1/2 phi dot 0 plus, and here I'm making use of the fact that partial of phi with respect to xi is pi 0. We've established that here. So I have okay, so this includes all the terms in the Hamiltonian density. It's something you just have to check carefully and make sure you didn't leave anything out. Okay. So H, I have pi 0, phi dot 0, plus pi I squared, plus 1/2 phi dot 0 squared, minus 1/2 partial phi 0 with respect to xi, partial phi 0 with respect to xi. I have minus 1/2 phi dot I, that's the phi I squared. And notice from this boxed equation just above us, phi dot I, this is equal to pi I. Okay. Now I have plus 1/2 partial of phi I with respect to xj, partial of phi I with respect to xj, minus m squared over 2 phi 0 squared plus m squared over 2 phi I squared minus 1/2 phi dot 0 squared minus 1/2 pi 0 squared minus phi dot 0 pi 0. Now you may be worrying about a little bit ordering ambiguity here or anything else like that. It doesn't matter. We're doing the classical thing right now, and you could see that we're okay anyway, because, you know, phi dot 0 is pi 0. Okay, now let's look for some cancellations. Okay, first of all, I left off the indice over here. So this cancels that. That's good. And the 1/2 phi 0 squared cancels this over here. Okay, So we got some cancellation, not a huge amount. Okay, so h is equal to, okay, I have pi I squared here, and I have minus, okay, I know there's something wrong here. Okay, I'm going to come back to this term because I know it, so I'm doing something wrong there. So I have minus 1/2. This is the gradient of phi 0. Okay. This term over here, I left that. This is minus 1/2 pi I. So that cancels that. So I have 1/2 pi I squared minus 1/2 that. Okay. Now I have plus 1/2 the partial of phi I with respect to xj squared minus m squared over 2 phi 0 squared plus m squared over 2 phi I squared minus 1/2 pi 0 squared. And this agrees with Borkin and Gell. And then we can write this in covariant notation. H is equal to minus 1/2 pi mu, because we'll get the minus, when mu equals 0, we'll get minus 1/2 pi 0 squared. And when mu equal I, there's going to be a negative sign. So we're going to get 1/2 pi I squared. That's good. And then I have minus 1/2. This is a 4-dimensional gradient. I'll put a vector on top of it, but del phi mu dot del phi mu, because I have the 0 term of this is minus del phi 0 squared, which is good. And then the I term would be a plus 1/2, and that's exactly what this is, phi I with respect to xj. That's del and phi I squared. So this is a 3-dimensional gradient, I believe. Okay. Well, yeah, it's a 3-dimensional gradient of each component. And then I have minus m squared over 2 phi mu. And again, the mu equals 0 term gives me the phi 0 squared term. Mu equal I changes the sign for the phi I term. So this is what we wanted. I'll box this equation. That's our Hamiltonian density. Now, finally, we want to get the Hamilton equations of motion. And here we can use the subsidiary, or at least verify the subsidiary condition. And we want to reproduce the original wave equation. Okay. So our first Hamiltonian equation of motion is phi dot mu is equal to the partial of h with respect to pi mu. Okay. And so let's just do it component by component. Let's take the mu equals 0 component. Okay. So the partial of h with respect to pi mu You can use either one of these, but you can see that it's going to be minus pi 0. So this is, well, let me do the other side first. Phi dot 0 is equal to minus pi 0. Okay. So now this implies, using our boxed equation from a while ago, we have, we can write this as, well, just transposing, we get phi dot 0 plus pi 0 equals 0. And this implies phi dot 0 plus, and if you remember a while ago we defined this equation over here. We have this equation which defines pi 0 in terms of the spatial divergence. So I can write that as phi dot 0 partial of phi I with respect to xi equals 0. Covariantly, that just becomes the partial of x nu. Oops. The partial of phi nu with respect to x nu equals 0. And so this is our subsidiary condition. We've shown it's consistent. Okay, so now let's take the mu equals I. So now we get phi dot I is equal to the partial of h with respect to pi I. Partial of h with respect to pi I is just pi I. And if you again go back to our box conditions, that's this one over here. So we're okay. So we've just, with this equation over here, we've just reproduced the subsidiary condition in our definition of canonical momentum. Now, the more interesting equation is pi dot mu equal minus the partial of h with respect to phi mu. So again, let's do the mu equals 0 component first. And we're going to get the, need to make this dot a little bigger. We're going to get pi dot pi dot 0 is equal to minus the partial of h with respect to phi 0. Okay, so now if we go back to our box equations, we use this. I don't want to use that. Pi dot 0. I always get confused on this one. Okay. Partial of I with respect to xi. So because we have that subsidiary condition, basically we have pi from this equation over here. Pi 0 is equal to minus phi dot 0. So pi dot 0 is equal to is equal to minus phi double dot 0, second derivative. So this should be a... Every time I do something on this thing, it just... I don't understand it. Software. So I want pi dot 0. Let's put a minus sign here. Just took the minus sign from one side to the other. So I have phi double dot 0 is equal to the partial of h with respect to phi 0. Okay. Now let's calculate the partial of h with respect to phi 0. And the first thing I want to do is make it a little easier. If we have a term like minus 1/2 del phi mu dot del phi mu, I can integrate by parts and just make that 1/2 del squared phi mu times phi mu. Just makes it easier to differentiate. Or you could just work with this and take one derivative here and take the del's out. Either way. So let's go back to our Hamiltonian density. This is the term I'm working on here. These are pi's, so I need the phi terms, these two terms here. So now I get that using this, the partial of h with respect to phi 0 is equal to del squared phi 0. Basically, when you take one derivative here, you get this term, and then move the del squared onto that, and you get a half plus a half. So that, and then from the Hamiltonian density here, this is minus m squared over 2 phi 0 squared. So the derivative of that is just minus m squared phi 0. So finally, our equation of motion becomes phi double dot 0 is equal to del squared phi 0 minus m squared phi 0. So that's the mu equals 0 equation of motion. And if we go back to our wave equation, and you look at the mu equals 0 from the wave equation, the mu equals 0. I'm not going to scroll all the way back up. You can do it, but you're going to get box plus m squared phi 0 minus the partial with respect to t, partial phi nu with respect to x nu equal to 0. And again, this is equal to 0. That subsidiary condition. And so this equation is just phi double dot 0 minus del squared phi 0 plus m squared phi 0 equal to 0. And that's the same as this. So we're okay there. So that's one equation of motion. I'll put a box around that. And then for mu equals I, we have the partial of h with respect to phi I minus that is equal to pi dot I. Okay. So once again, using this again, pi dot I is phi dot double I. So I'm left with phi double dot I is equal to minus the partial of h with respect to phi I. Let's go back and look at our thing. We again have the same thing here, only now we have an I, and the same thing here, only now we're going to have an I. So I'm going to get get a minus del squared phi I plus m squared phi I. You can check the signs and you'll see I didn't make a mistake. So we're now we're going to get phi double dot I minus del squared phi I plus m squared phi I equals 0. And you can verify this comes from the wave equation also. Notice each component has the same each component really solves the same equation. Time derivative minus the Laplacian plus m squared equals 0. So that's like when we do like the Dirac equation, each component solves the Klein-Gordon equation. So here, this is our basic Klein-Gordon equation, and each component of this satisfies it. Okay, so that's all I have to say today. I will have another video on a problem in Schrödinger, and I think that will wrap up lesson 3. I was thinking of doing a video on the canonical quantization of the Schrödinger equation, but we've already seen that in Schrödinger Chapter 1, and I don't think it's necessary to go into the detail on that. So I think I just have one more problem to solve, and then before we go to week 4 in Schrödinger's book, my plan is to add a whole new deep dive week of videos. I'm titling it 3.5 on my Piazza webpage, and it's going to be on symmetry, gauge invariance, and Yang-Mills non-abelian gauge theories. It's just all on a classical level, and it's interesting stuff, and Noether's theorem as well. But it's not treated in Schrödinger until much later in his book, and most of the other books treat it quite early. So I want to have like a quick deep dive on it just so that you've seen it. And I'll see you next time. Thank you very much. Bye-bye.